Welcome, I'm Bill Wake. We're working on a programming language called Tenth. We've finished the interpreter and the compiler, and now we're working on fleshing out all the primitives, and we're in the middle of operators, so we'll focus there today. Excuse me. All right, let's see. We left off, divide and mod. Let's pick up with min and max. All right, let's see. I did make a change overnight. I talked about dividing everybody up into separate files, and I did that. So arithmetic operators are in one file, and control and IO and relational and stack. I didn't write any new tests. I just split around the files and rearranged. So arithmetic.s and arithmetic tests. All right, now the tests, we have an operator, so it's pretty easy. If we do min b, I guess BA is minimum. Ugh. I'll get there. All right, and our data is these two. So 58's the smaller one. And we're assuming there'll be a min. Now this should not compile. Yep, no min. All right, let's get arithmetic up here. Yeah, actually, I'm going to pull both these a little further to the right. Okay, so global mod, set global min. Yeah. There is a lot of similarity, but I don't think dropping in these things will do it. Anyway, min with okay. Now I don't know. There may be a quick way to calculate this in ARM64 min function. Min x64 function. Well, that doesn't help any. Calling functions. Nope. Well, it's not that hard. Okay, so we've popped A and B. Let's make x2 make it x0. Now, I remember there was C set. Let's see, is that the one? Conditional select, that might be it. The value of this first register condition is true, otherwise the value of the second register. Yeah, that's pretty close to what we want. So if we compare them and it's true, then we get the one else the other. Okay, yeah, that's the kind of forward thinking we want here. Okay, so we want to compare these two. Compare x0, x1 is the top of the stack. I don't guess it doesn't matter really. Well, we'll compare x1 to x0. You're going to have more trouble when it's less than. Okay, let's see. So um, we want to conditionally select x0 is, how's this work? Okay. Well, it's the two numbers, x0 or x1, depending on which one is. I wrote a page number down, 144. Here we go. So if it's, let's make sure the thing works the way we think it should. Well, oh, I lost it. Okay, I think if it's less or equal, signed less or equal, we should take the first. Well, I guess let's compare x0 to x1. x1. If it's LE, LE. Okay, so if x0 is less than or equal to 1, pick LE, pick x0, else pick x1. I think that's the minimum. Oh, I guess I should actually let's do it a little different. Let's a little enthusiastic here. We haven't seen our test actually fail properly yet. Let's do that first. Mod is already defined. Okay. Stuff like that is why we do that. Okay. And we should get a fail in our arithmetic tests. Oh, I didn't add the test. Yeah, see? I think arithmetic is already covered by the fact that this is arithmetic test.s, and it's got arithmetic tests there. All right, here we go. VA is minimum. Well, that's going to be interesting. I guess we pushed 142, then 58, and then the top of the stack is already 58, so it looks good. So let's make a test. I still want to use this, but well, maybe we'll instantiate our code into the test. Sometimes that's a good way to do it. I think we'll see max come out the other way on the first run, but we'll make sure this test passes too. Okay, so we haven't messed anything up with our test, so it still pulled the top value. That makes me wonder if I understand AB. Let's look at this thing. That's in assembler macros. Pops register 1 first, then register 2. So it really is A, then B. Huh. Okay. So X1's the top of the stack. And is the lower one. Okay. We compare them. I think we're okay. We'll find out on this one, though. See if I can do all these trivial things this way. 142. We need this. And then in arithmetic, we'll need mod, max. And let's leave it the code for minimum and just make sure that that does not work for maximum. Okay, so that should give us a failing test. What do we got to do? Global. Okay, there's my failure. We expected 58. We got we expected 142. We got 58. All right. And then this, we want the one that's greater or equal. Okay, good. All right, and we'll need to put these in main as well. Okay, let's make REPL. 2, 3, min dot should be 2. Okay, 2, 3, max dot should be 3. Good. Okay. All right, now we come to the one that's different. So divmod gives you, well, it takes the two numbers and puts the dividend, the dividend first and the remainder second. I think I'm using dividend correctly there. All right, but I think that's different enough that we can't use that little standard test we developed. It's going to be a variation of it, so let's take it as a base. All right, so this is divmod puts mod on top, then dividend. Okay, so we got test data stack. Oh, I renamed that. Test data stack L data is 142 and 58 on the stack. And then the routine to test is divmod. All right, and then our assertions, we expect let's see, so 142 mod 58. So that was 116.26 was the mod. So we expect 26 on top of the stack. And we popped it, so now we can test the second one. All right, it's that extra test that kind of makes it. All right, and that was 2 because that's the dividend, the division result. Okay, now arithmetic, we don't have a div mod operator. And I almost think it's nicer to do this in a way with A percent B, A to B, C. And sometimes I think it's, if I mention the whole stack, or, the top three on the stack, including the first one that's not touched. Okay. Two values, then pushes their quotient. Oh, that's the word I'm looking for. Then remainder. All right. And we need to call that div mod. Oops. Yeah. And I will put min. I don't know. Doesn't matter. Probably doesn't matter. I did screw that up though. Okay, and I expect this to fail. Not quite like that. Div mod. Max. Data pop compare. Yeah, I totally duplicated that somehow. I'm trying to save myself typing div mod again. So okay, arithmetic. Oh no. Oh, we don't have the test in our list. I really wish I had that separate section that I could write. I would love to make my test header, test start, write the BL jump to this in the main routine, but we just can't do it. Let's see what that thing's called. Okay, and this should probably blow up the stack because it's accessing the zero somewhere. That's no good. Something should go wrong. Definitely not nothing should go wrong. Okay. Yeah, so both fail. We got 142.26. Right, so I guess it put the minimum or maximum on there. And then the remainder. We expected 26 and 2. We got 142 and 0. Oh, it popped off the 58 and left us working on the guard word we put in there. Okay. Which sounds quite plausible. All right, and div mod. Now, let's find div and mod, see if we can combine them. Well, actually, div mod kind of had the div as well, right? So let's push that in here. Okay, so mod, the quotient is in x2. It's x0 divided by x1. Then we did the m sub thing to subtract it back out to get the remainder in x0. But we still have, now I guess we want x2 first and then x0. We said the mod is on top, and that's an x0. Okay. Good. And let's go to our main. All right. Now, abs and neg are unary, and we have two of them, and we kind of have three of them. We haven't tried using these outside of the arithmetic package, but maybe that's doable. All right, let's do absolute value first. Well, I can see I want more data. Let's put another value there. And I guess we'll make a unary op test. Okay, so I'm just going to push L data plus 16. That gets us to that negative number I just put on there. Test name routine to test expected. There's only one push because it's unary. Routine to test, pop, check that it's expected. Okay. So I think this is a unary op test. Yeah. Okay, name. Neg minus 7 is 7. I don't know. Kind of use those names A and B and C. Okay, we need an operator, neg, and expected value 7. Okay. All right, so we'll need a neg. Again, I've got kind of a junk routine here as far as neg is concerned, so I'm pretty sure that'll fail. Did I call it? Yeah. It's popping 2 items when there's only one on the stack, and then that can't be good. All right. Implementation. Okay, we really just need to pop the one item. And then, I don't know, is there a neg? Neg. Can't find by word. Compare negative. negate. Negate's an optional shifted negative. Okay, we don't need to shift. We just do neg x dxn. Pretty minimal. All right, and then I'm going to change that test a little bit. I'm going to say neg a goes to positive a. And then I'm going to write pos a goes to negative a. Neg, let's do, oh no, it doesn't work that way. Do I care of that test too much? Maybe I give it a little extra boost with, let it choose the offset. Name, test name, data offset. In the routine to test. Okay, so data offset is 16. And I think I'm allowed to say offset equals 16. And then this one, offset equals 8, neg, and then the value is 58. Okay. Now, sometimes I do this thing. I run these tests sometimes. Usually TDD, I'm just writing a test I expect to fail and then pass and then fail and then pass. Sometimes you've implemented something that seems more general than your test really tests. So I put in these tests. I call them confirmatory or confirming or sometimes guardrail tests, but they're there to make sure that stuff that really should already work does work. So I expect this test to just run green. And if it doesn't, then I've got something wrong. Okay, well, okay, apparently they don't allow named ones. All right. Yeah. I meant something in the test. Okay, like that. X equals minus 58. Oh, yeah, that's true. I said it should go to negative, and I didn't make the expectation that way. Yeah, and if it doesn't pass, it may be your test is written wrong. Arithmetic, negative 8. Okay, good. Name equals values for default values. Oh, no, I'm pretty sure the GNU assembler lets you do name parameters. But yeah, if you want to define a default value, you can use the name equals value, and we've done that, so we know that one works. All right, let's see, back to main. This is neg. Well, that wouldn't affect that. Okay. And I guess we'll just make REPL. 10 neg should be minus 10. dot. Yep. Okay. Did I commit it? No. All right. Let's do the clear. Neg A. Well, abs of neg A goes to positive A. Abs of pos A goes to positive A. Okay. Abs of neg goes to positive, that's 7. Abs of positive goes to positive. All right, we don't have abs, but we'll get it soon. Oops, X1 is not a temp here. Okay, and this is, are we back to C cell? Conditional set. Select negation. What's that do? Returns the value of the first register if true, otherwise the negated value of the second register. Okay, I think that'll work for us. CS neg. All right, so we've got a pop AB. So A is the top, X0, X1. All right, and then we'll compare the, oh no, what am I saying? We need X0. We compare X0 to 0? And then we want the CS neg. If the condition is true. Okay, so X0 is going to be X0 or X0 if it's greater or equal. Okay. I don't know, a touch clever maybe. All right, so we compare X0 to 0 if it lets us. I think it will. If it's greater or equal to 0, we return X0. Otherwise, we return negative of X0. Okay, which will be positive. Well, I'm just going to do a ret here first because we didn't really run that test yet. Neg's already defined. Oh, this is supposed to be abs. Okay, I didn't put my tests in. So important to see a failure when you should. Okay, there's that. Yeah, so right now it just does nothing. So whatever's, if it happens to be positive, it passes. But let's take out that return. This conditional select one's going to be helpful when we get to these relational operators. Oops, am I back too far? Yeah, there we go. I think, yeah, you need to use the zero register. And I think this is one of those places the assembler's smart enough to say, oh, you said constant zero. We'll use ZXR, you know. Okay, so that was abs. Three, yep. Okay. Let's commit that. All right, that's the arithmetic ones. Okay, so the logical ones, I mean, we have been in binary ops and one unary op. We have the same thing in relational. Does it print negative values? I believe we did, but let's make sure. Whoops, make REPL 3 nig print. Yep. Yeah, we did a little extra little work for that. Okay, good to check though, because it's easy to have lots of intentions. At least I do, and some of them I've actually already done. All right, logical operators. We have time. Oh, we're doing well. Okay. So logical. And I'm of two minds on how to do this. I think we could. One approach would be to just copy these over to the other one and modify them to work with the local area, which means really just copying the data they're working on too. That's probably the easy way. The more complicated way, and I don't know if this is a good way or not, but we would have to put these macros somewhere everybody could get them, which we have core tests, and I think they could go there, except normally you wouldn't put data in a macro file. And so, like, who's going to declare this data? But it's doable, maybe. I mean, if you just say you got to have something called test data stack and you got to have something called L data. And maybe he should be local. Okay, test data stack referenced. Why are you referenced? Oh. Okay, so what we've done, we've, well, we just made the name local. Make test data stack name be local. Okay. And so I think if we said you got to have a variable named L data test, whatever that is, and L data to use these macros, I guess that's probably kind of okay. We'll document it, So I think if we did that, we could move these up into core test macros. Let's try it. Because I think if you don't use the macro, then it shouldn't expand and it shouldn't create a reference or anything. I may be wrong, but we'll try it. Okay, now it's in core test macros. Let's take it out of here. All right, and this, and make. Yeah, so much for that. Who's complaining? Oh, So really, it's not comfortable with that macro having a name even locally. No, I don't think we can put them in the macro file because, well, could we? I was going to say we couldn't because then every test will have its own, but we don't really. Our tests don't rely on each other, so yeah, let's try that. And there is a way to say you've got common data across them if they're different sizes and different files, it adjusts them to the maximum. But I think you're right because we're not building this stuff anywhere different. I mean, we don't build two tests together, so it shouldn't be an issue. Okay, there's the data. Let's see what happens. Oh, still doesn't like it. Let's look at arithmetic posts. Okay, so it creates the macros. Wait a minute. And this is arithmetic. Okay, next, arithmetic tests. That's the one we want. Okay. Oh, now these haven't expanded yet. Complaints about, VPC and load address. Oh, those are in assembly. Let's see. Okay, yeah, maybe we just got them in the wrong order. Let's do that. That seems better anyway. Okay, VSP, where's that defined? I thought that was in core defines. Oh, it is in core defines. Wait a minute. Core test.macros. Let's do that. So our macro, so our our predefined registers or reserved registers don't substitute in the macro file if it's not included like this. I think to include this really kind of weird. Ugh. Arithmetic test.post unary op test while in a macro instruction. Invalid operation for instruction. We still don't have it. Do we have to include it in? Okay, let's open assemble.macros. We didn't really do that define thing up here. If not defined, Simpler macros define. No, I'm doing that wrong. I guess I'm not doing it wrong. So I think core tests, he's going to need the assembler macros. Well, let's do the same thing for him. Now, I thought we were making sure. So when we include assembler macros and core defines, by the time we get to core tests, I would have thought those would be defined. But maybe we have to include them directly. Yeah. Well, this is why the copying approach is easier. Now, I don't know if I'm going to get double definitions now. No? Okay, let's take out the instantiation here. He still doesn't do VSP. Well, no, VSP should be in core defines. That's all the register stuff. I don't know. Are we making progress? This doesn't seem right. So it's complaining about VSP. It's complaining about data pop. So I can include assembler macros too. Same kind of assumption. I guess they can come first. Yeah, it just doesn't seem like it likes that. Invalid operand while on macro instantiation. I don't know. It seems like it has it. I'm going to revert it and do it the sort of easier way. I'm kind of on the line anyway, because when you're in a test, it's kind of a pain if the test setup is in some other file and, but I don't know. Kind of don't like duplicating things everywhere either. We don't have a logical yet. Okay, let's make a file for it. New file. Almost did it wrong. Okay, he's going to kind of look like this. He's going to need similar stuff. I don't know if he needs REPL macros, but okay, he defines his local stuff. He's got his prologue. This is logical tests. We haven't defined any definitions yet. I think I pasted stuff in logical. Yeah, these really go in logical tests. Okay, and then we need to work on our make file. Logical. Everybody kind of needs these. I think we can let it tell us what else it might need. And then we put these down here. / logical tests. And then logical tests, let's take that out for a moment. Okay, that should make. Okay, logical tests needs print. And print, is that in C-like? Yes. I put that in the wrong place. Okay. Logical test, don't do anything. All right. Yeah, it's annoying to me. I don't know. I guess if it had worked, I'd have been happy. But it didn't seem to just click together, and it seemed like we're coupling things in more and more. I don't know why it wouldn't work, but because it seems like if those things are defined for substitution, it should have substituted them at that point. Even if the macro itself then would say, X19 or whatever, but that seemed okay. But I think this is much simpler. It's a little more redundant, so it's a little duplication across tests, but I can look at each test and know in context it's right, so I'll take that little dab of loveliness. Okay, let's see. So our test, logical tests. All right, so I guess we need a test. bin op test. Test name is and puts A and logical and B. On stack. Okay. And then second argument, routine to test. Well, I just hope and is available. Oh, might not be. Yeah, it may be something like that because it's like the macro didn't expand when you define it. It's not going to expand until you're compiling the other one, but it seemed like between them they couldn't agree on what the core routine things were. So I don't know why, but yeah, it was probably something like what you're saying. It just it wasn't real code, so it couldn't get done one way. I'm going to call this and routine because and is an assembly language instruction. And expected value. Well, we got 158. Let's get that 158 clear. 158 and 42 equals 10. Okay, and in binary. Okay. Well, I guess 42. Let's look at it in binary. 158. Okay. That's got to be like 64s. No, 120. Wait, I did that wrong. Clear. 158 base 16. Oh, okay, 9E. I guess I can find a pen here. 9E, and then clear 42. Clear 42. 16 is 2A. Okay, so, well, 9 versus 2, clearly they don't overlap because 9 is 8 plus 1, and 2 is 2, so those don't overlap. E and A, I guess E's 1 up to F, so yeah, one below F, so it's going to have most of its bits set, and then A has 10, so 10 sounds right. Yeah. Okay, so let's expected value of and is 10. Okay. Oh, let's get this up there first. And logical, well, he's got to be like arithmetic and include some stuff. Okay, and place top 2 with by logical, was it conjunction? I'll just say logical and. Okay. That's that. Test should be good. All right, so this should, well, it should run and fail. Yeah. Push and assert equal. Oh. Core defines. Logical test. Oh, he needs AS unit and where's push? Stack, I guess. Okay, logical tests. We got 58. Expected 10 because we didn't do anything. REPL. No, I pulled out a stack one that has all that. Let's see, make sure we. Yeah, so push word address and then the routine itself, and then push 0, push 1, and dupe. Okay, so we've already got one done. Okay. So it didn't do anything. Yeah. Okay. That's not unexpected. And I think, well, these all have such similar structure. Pop them and x0 equals x0 and 1, push it. Yeah, I don't know if we can just. Sometimes it's a couple lines, sometimes it's a little bit different. Yeah. Okay, but that passed, right? Yep. Okay. Let's do or. And we'll leave it wrong. All right, 158 or 42. All right, let's clear this out. 10, 158 or 42 equals 190. Okay. Can't remember everything. There's the failure we want. Get 10 instead of 190. And then I don't know what the his search isn't very good. I don't think I can or yeah. And I don't think I can do quotes. Okay, I know Eeyore is in here. Not the little donkey, but exclusive or. your vector and, okay, and or R. Bitwise inclusive or an optionally shifted register. Yeah, that sounds like it. Oh, or with register. Okay, I guess that makes sense. Should pass. Yep. All right. Let's add these to main. I think they show up like that. I almost could see the C operators for those. All right, so somewhere there's a README. Haven't done those two. Okay. Okay. Let's do XOR first. Clear. Do I have XOR? Yes. 158. It's going to be some very negative thing. Back to base 10. Clear. 158 XOR 42 equals 180. How can that be right? 16B4. Because 0 is 0 should be 1. It's like it's not doing the whole 32 bits. Clear. 158. Sorry. Clear. 158. Base 16. This is weird to me. XOR 42 base 16 equals B4. All right, clear. 0 XOR 0 equals. Is that, how is that right? Isn't 0... I thought XOR was 1 if you're different and 0 if you're the same. Is that right? Or is it 1 if you're... Oh, okay. That'd be that. Okay, 180. I'll believe you in the calculator over me. Okay, XOR puts that. We don't have the test in the list. Let's get that first. I believe this is EOR. Well, we'll make it OR for now to fail. XOR routine. Okay, should fail. Well, yes, fails. We expect 180, gets 190. And it passes. Okay. And in main, well, I'll anticipate a little bit here. XOR not. Okay. No, not. This is our unary. Okay, 150. Whoops, clear 10. 158. Hex. 1's complement should have 0110 00001. Okay, and in base 10, that's a, well, that should be negative. Huh. Let's try -7. Isn't that the other value we have handy? 7 minus 2's complement. Okay. 1's complement is 6. Okay, so -7. Yeah, I can't negate that. Not subtracted from whatever gazillion. All right, so we'll use the other one. -7 negated 1's complement. Right, so 1's complement of 6 should be almost all negative. That. Okay. Put it back. It takes 2's complement. Should be 1 higher. Okay. All right, so unary out test is test name data offset 0816. Not routine -7 goes to 6. Okay. So the key thing is the 1's complement and the 2's complement are different. And 2's complement is 1's complement plus 1. So it all seems consistent. All right, now that's fine for that. Let's get the test up there. It's unary, so I'll give it a little extra room. And logical. Logical not. Okay. And I'll just return. Yeah. I guess I'm glad it complains about the error. All right, we get a fail, -7 instead of +6. Okay, because it left it untouched. All right. So this one, well, it's going to be just a data pop. And then push, but the not operator. I don't know where that table went. Neg. That was the one we did. Move not bitwise inverts a register to the destination. MVN writes the bitwise inverse of register to the destination. So NVN destination is that okay? I guess MVN x0 x0. Okay, logical, good. And let's add it to the main. Oh, I've done these badly. And routine. Make sure we called it that. Yes. Oh, okay. REPL doesn't have logical. Okay, so if we do 158, 42, and boom, okay. Bus error. All right, let's track this again. There's ampersand. It's our only ampersand. It calls and routine, which is logical. One 42. That sure seems okay. Okay, LTV. Ripple out. We'll just see where it blows up. Run. 42 and bad access in the and routine. X19 minus pound 8. I don't know. Have a special meaning for the input. I don't see how it would, right? I mean, we're just reading we're reading, oh, you mean in the main? I mean, it seems to be calling What's x19? Data stack plus 16. X19 minus 8, which is... Oh, does it? I sure wouldn't think it would. Well, no, you're right. Oh, yeah. Is that... Well, when you do a Unix command, ampersand, right, you get the switch to a separate process thing, but... Well, let's do a little research, I guess. Unix read of ampersand. Yeah, this is ampersand at the end of a line says kick it off in a separate process, and you can resume, yeah, Control Z, BG and FG switch around. But that's the shell making that decision. And also we're dying in the and routine. It's, I don't know why X19 is the data stack. That seems correct. And plus 16, we've pushed two things on it, so it should be ready, at the 16th byte after. X1. Bad. Code 257. Address 1386E. LDAR X1, X19 minus 8. Well, yeah, fair question. Let's change it to and. No. Something's weird there. LDB ripple diode. Bad access. Address 100386E. Well, reg read X0, reg read X1, reg read X19. Okay, that's data stack plus 16. Where's data stack? Well, okay. It could be let's go find it. Maybe I didn't put it in the data section. Stack.s. Data stack text. Okay, that seems okay. All right, let's find it in here. Data stack, init. I don't know what this is. Start. Oh, there's our routines. And they all look the same as all the other binary operators. Well, let's check the binary operators then. Run, yes. 158.42 plus. Print. Which puts me a little loss. LDR X1, X19, pound minus 8. I mean, I gotta think all these binary operators kind of look like that. Divmon max. LDR X1, 19 minus 8. Yeah, I mean, that's... Yeah. 158.42 or dot. Data stack plus 16. Okay, let's go find data stack. There's add. He looks the same. How can that? I don't understand how it's dying on this load R when. Well, here's add. LDR X1, X19, pound -8, bang. I mean, more or less the same except for this line. Store X0, X19 plus 8. Return. And yet it's dying here. How much memory for the primaries? Oh, good. I see. Yeah, yeah. No, I was thinking the data stack is huge, but I don't know what we reserved for. It's really for, yeah, for primaries. Good point. Is that in here? Probably in dictionary. That's not a lot of bytes, is it? 300. Well, 800 would be 100 words. I don't think we have 100. We might have 30. Oh, and it's got to take all the string contents of them. Okay, yeah, good theory, I think. Huh. System dictionary. What's meta list? Oh, that's just the meta ones. That's a very small list. This one? Okay, ldb repo.out. Run. Let's try not. -7. No. 7 neg that. Boom. Okay, bad access. Address 38AA. I mean, he's using X0 and X19, right? So it's got to be one of those two registers. He's loading X0 from X19, so it's got to be something about this. Yeah, we should have one value on the stack, 7. We negated it, and then we accessed it. Okay, so let's do mem read C200. And let's make it 700. Okay, so XD27C0. Well, I started just when it got interesting, didn't I? Let's start from B0. Okay, C0 is here. Well, where's my data? So if it points to 2, oh, there's my data. Yeah, that's -7 because it reads backwards. 2D. So this thing is C0. If you take away 8, you're at B8. Load register 0 with the contents of this B8 sure seems like it would do the right thing. Well, it's not blowing up on the identical code in add, right? So I don't know. Maybe there's something environmental. All right. Let's take a break. And while we're gone, the answer will magically appear. I hope. See you in 3 or 4 minutes. Welcome back. All right. So, the problem is with the logical file. It seems everything else seems to work. That's good. Yeah. Is it? I got text here. Where's the data? Okay, that's that. What about the? It's not the test, right? There's data. There's text. These are read only, so there's no writing to them. Missing a text after the data. Right. Well, although you could probably spin up something. I think you default to text at the start of a file, but I'm pretty sure I declared it in both. Yeah. Um, well, my other thought was go back to main. Let's move these up. I mean, these down here are failing. Let's move this up here before this. Why it should matter, I can't tell. Unless there is some space thing. I mean, that was a good thought. Just turn out it didn't seem to be the issue, but it sure seemed like a good candidate. Okay, so it's really the REPL that's going bad. Okay, 158, 42, and oh, have I? Oh, I changed it. Okay, 158, 42, and boom. Huh. Well, let's go find that and again. We saw it somewhere down here. I mean, it's not a bad. I don't think that's the error you get if your instructions are off. But my, that's a big pile. Any queue, push through a dupe. Okay. Start to the entity and routine. 386E. Is that a good boundary? I didn't do two aligns. Let's try that. Oops. Put it back to what we think it should be. Take this out. Logical. Yeah. Yeah, there's no BLs in these. So, okay. So, yeah, I did neglected to put a line 2 after a text. Oh, boy. Okay, I did there. Wowzers. That means I'm going to check these other ones too. Now, the thing is, if if the file before you happens to have everything right, then you sort of come up right. But let's fill in all these. Well, that's got that. Most of them appear to have it. Line 2. I think this should probably be P2 line 3 would be safer on the data front, because that could screw you up. Yeah. I don't understand why it wouldn't be the default. I mean, there's a running theory that Apple hates us. Maybe this is a sign of that somewhere coming out. I mean, really, the thing is, they don't want you, they apparently don't want you really building much assembler. And I understand it in a sense because um, how many times have they changed architectures? You know, you had 68K. I don't know if you might have had a couple of 68020s or something, some variations in there. And then at one point they were going to run on alphas or something. I don't know if they ever did. They certainly went to Intel, and they certainly went to ARM and various flavors of ARM. Um, I guess you had ARM 32 at some point on things, and now ARM 64. PPC, yeah, that was a good one. So they've changed architectures 4, 5, 6 times, and they know if they change the architecture and it breaks because you've been doing assembly stuff, they're the ones that have to kind of get the blame, even though you're the one with the problem, really. Or they have to, they have to emulate or whatever. It just gets to be a barrier, and they know it slows you down moving. Sometimes you need it. There's some cases where you just can't get the performance. But yeah. So I think they, not just them. There are other companies out there that have actively discouraged assembly programming, not as dramatically. I mean, they do have this assembler. I don't think I loaded it from anywhere. It was just built in. The one they shipped with. All right. So ACP add alignment at start of file, and I think the alignment, the problem is if one file gets out of alignment and then you stick it in front of the next file, right? It just puts it at the next address, and it doesn't really know. Um, but we'll take that. Okay. Well, that was the logicals. That wasn't horribly, horribly bad. Let's get this updated. Not an XOR logical. Well, XOR and not. All right, let's do it that way. What was the bad thing in front of us? I don't know if we can tell, but yeah, just weird. Okay. And it could be like some of these cases where you have put read-only data in there, they do get misaligned at the end, so you do have to kind of recover them. But all right, so it's Q4. From a point of view of intellectually challenging, I think relational it's a bunch of binary and unary operators that don't look too complicated. The stack stuff is a little different, but it's all just, am I pushing? Am I popping? Am I swapping? What am I doing? Um, I don't think it's too tricky. But the control stuff, I think that's interesting. So I kind of I pulled up some stuff we had earlier. Let me get that up. I'm going to switch gears to that. I just don't want to wait till Thursday. It seems harder. So let's tackle the harder stuff first. And also it's more important in a sense, like, if you had operators, well, you have operators, you can do some things, but if you don't have loops and ifs and stuff like that, you're in trouble. So this is code we'd sketched out before, and I don't know if I can let. Well, all right. So the way this works is the bold ones on the outside. They're what do you want to generate in your code based on the if and the else's and the ends. Okay, and so the way I do this as a compiler person, I would say, what code am I trying to generate for that if else end statement. Okay. And I know I have to evaluate A first because that's what feeds the if. So I'm going to evaluate the code for A, and then I'm going to do the if test, which says if that thing is false, then jump to the end. If it's no else statement, just an if end, jump to the end. All right. And then I have the code inside the if. Well, the code inside the if has to come after the if statement. So I kind of know that the if statement should generate jump, if else, and pointer to end. Okay. But I also know I don't know where the end is yet when it's time to generate that. So that's the kind of trickiness. So I'll decide on the assembly code, then I'll look and see if I can generate it. And then when I have something like this with two things, I got to make sure that the if I have the path if end or the path if else end, that if end generates the code on the left and if else end generates the code on the right. So it's a little trickiness. Now, if is a little more, it's kind of a complicated one. Let's go forward. I think repeat until is kind of the easiest one. So a repeat until, you're going to run through code until the repeat is where you come back to. So it's sort of like the label, the start label over there on the left, and then the code inside the loop, and then the until statement. So the start label, we just put the start label in. In our case, the code to generate that is, if you see the repeat keyword, then you push the code address to the stack. So that code address is where you're going to jump back to. And you're putting the slot in the secondary as the place you want to patch. Not even that. No, you're just putting the address of the secondary as the thing you want to jump to. Okay. Then the code inside the loop, that's the ... That's whatever that code is. It generates itself. And then you come to the until, and there should be something on the stack. So we're going to do a jump if false back to that start loop. And we get that value by popping the control stack. So if you recall the control stack, I think it's only like 10 deep, but that's for nested structures. So we push the address of the start, and then when we get to the until, we pop that address and patch that into our if false, jump if false. Okay, so the jump if false instruction is followed by a word that points to the secondary address. And then whatever code after the loop, we just fall through or don't fall, either jump if false or fall through if true. Okay. And so that one's pretty straightforward. All right. Let me go back to the if. All right. So the if, we want to jump if false somewhere, but we don't know where it is yet. So we just put our address on the stack, and we'll come back and patch where it says arrow end. So instead of, when we're generating it, it'll be jump if false -1. And then at the end, we're going to come back and patch that -1 and turn it into arrow end, go to the end. All right. And then the else clause, we're sort of like hijacking the if. So we need to put a jump before it because the end of the if has to jump to the bottom. Okay. We generate the jump. We pop the control stack, and that tells us where we're going to patch. Well, instead of jumping to the end, we're going to jump to the else label. Okay. And so that's what we patch. And then we generate a -1 after the jump. Because that's going to be replaced by the jump to the end in the end. And then put the current code address at the patch location. Okay. So I think that's saying it right. But we need to jump to the line after, the word after the end, the jump to the end there. So jump to the end gets the if clause to the bottom. The instruction right after that is the location we're going to come to on the else label. Okay. But the end is the thing that has to get patched, that arrow end. So we get to the bottom, you pop the control stack and get the patch value, and put the current code address there. So the address of the end is going to be there. Okay, I'm going to pop out so I can see if there's any questions. Okay. Do you push the repeat address on the stack every time, or you leave it until it says it's done? Okay. Yeah. So um, the thing is, and this is the part it's easy to get twisted on. So when you see repeat in your code stream, like you see the word repeat, that's going to be a meta word, and the meta word is going to kind of take over. Even though you're in compile, or you're in compile mode, normally you push a word on the stack. Repeat says, now I'm a meta word, I'm going to take over for you. I'm not going to let you just push my repeat on the stack. There is no repeat routine, or there's no runtime repeat. There's just jump ifs and else and jumps. Okay. And so we're going to build the control structures out of the go-tos and conditional go-tos, basically. So at compile time, you see the word repeat. It pushes code on this, an address on the stack, which is the address in the secondary that we're trying to create. And then when you keep generating code until you get to the until, and then until is also a meta word. It's going to say, hey, don't just store something on the address for on the stack for me, or in the secondary. Store this stuff instead. Generate a jump if false, and patch that start statement, and generate the patch value there. So it's kind of a one-time compile time deal. At runtime, the loop is more like the code on the left. The code we execute in the secondary is going to be the code on the left. We'll do something, the body of the repeat until. We'll at the end, we'll do jump if false, which means we're looking at whatever is left on the stack, the A I didn't put in here. And the address to jump to is start if it's false, because we repeat until it's true. So if it's false, we go back and continue our loop, and our start 2D routine will be fine with that. We have the jump if false already works. Okay, so this is the kind of it's almost like 3-level thinking you're doing. The the stuff that happens at compile time in the meta with the code stack and manipulating the secondaries, and then the I guess at least 2 levels. Then the second level is what happens at runtime at the interpreter, and so the repeat at compile time never repeats, but the code it generates is the target of a repeating loop, so it works out. All right, let's see. Until it's done. Yeah, it says there you pop the control stack after the until. That's correct. Yeah, so control stack is a compile time construct. And when you hit the until keyword, you're going to use up that address that's in there, and put it in the jump if false target, to jump back to here. And you need that because I might have an if else end around my repeat thing. So whatever control structure I make, the beginning and end, they have to be like nested parentheses. They have to undo, they have to make it look back to normal for the next control structure that comes along, or for the outside one, or and same thing for an inside one. If there was a repeat until inside, we would have 2 repeat targets on our control stack. This start and then the second one, and then the first until would do the topmost stack item, and the second until would have the next one down. So it's yeah, it's a little weird, All right, then I'm not sure what to do about while do. So one thought was you could do a while dot dot dot, and then repeat whatever you want, however you want to calculate the condition for the do. All right, and it's a similar process. I'm putting a start address in. I got to keep track of, and then evaluate the a value, and jump if it's false, and all that stuff, and then patch the jump after, and and so on. I'm thinking maybe a different wording would be better. If you said while expression do body then done, okay, then the expression is going to get evaluated after, well, it's going to get evaluated at the first. I haven't said what we're doing yet. Okay, so but this is what we'd have to specify in here, like what's going to happen with the while. Well, we need to push the um, the code address onto code stack. He doesn't like address onto the code stack, and Expr is generating its own code, so we don't have to do anything for that. And then do, let's see, we have to generate jump if false, and we we need to generate a -1. Well, we're going to push a code address on the stack. Push code address on stack, on code stack, or control stack is really the real name. Okay, because we're going to have to backpatch this end loop. All right. And then we generate a -1 just as a placeholder for the end loop. Okay. Then the body generates its own code. And then we hit done. We got a lot of work to do, I guess. So one thing is we're going to generate a jump. We're going to pop this one is start. We're going to pop start, and then put and then generate that. All right, and then we have the end loop. Okay. Well, I guess we're going to have to pop end loop or jump if false and start. Because jump if false is on top of the stack. So we got to make sure we pop two things. We need start before we need that. So it says you pop control stack after the until. Okay, yeah. I'll come back to that. All right, so we generate start because that's the next instruction, and then we don't generate end loop per se, but we catch where it is. Okay, so we have to patch current instruction address into jump if false. Okay, so I think that's the way this will go. But so I'm kind of working my way down the page and saying, at this point, what information do I have? All I know is my current address, and I'll just save that so we can come back to it. In here, I've done the expression. I'm assuming it's sitting there, whatever they want to do to get it on the top of the stack. And I'll generate the instruction to evaluate, but I don't know what value to put in there. Create a secondary call for the do one. Yeah, it would certainly be possible to do something like that. But the trick is, though, that then they would have to do, well, see, I don't have a way in the language we've generated, we don't have a way to kind of encapsulate the code block, like for the body, right? We would, if we did, like we could encapsulate the body of the expression in the body of the body itself here. We could pass those as arguments to a while method or a do method or something like that, but we don't have them. So it's it it would be an alternative model. And if you look at like Lisp or a functional language, that's more the approach they do. I mean, Smalltalk as well. Their bodies of code are blocks, and it's like a little closure that they pass to the if function. Okay, but I don't think we have the concept in kind of semantically in there to do that. And so instead, we're generating the code more like a compiler would do. Um, for do done ill sounded sections. Yeah, I mean, we probably could extend something. Yeah, maybe there's a way. Like if you, well, kind of like well, no, that's not really the same, is it? I was gonna say like define, you do colon and a word definition to define, and the word to define gets looked up in the colon meta word. But if it's a regular thing, like the repeat doesn't have access to the next word at runtime, I mean, you could sort of imagine something like that, I guess, that the repeat grabs the next word as its body. It's going to be a word that calls a function that is the body stuff, and that it keeps the word as a string and then looks it up in the dictionary or something and then gets the code from there. That there's some slight extensions you could do to what we're doing now that might be able to make that kind of pseudo closure. We don't really keep usually the trouble with closures is what they're closing is they kind of grab they pretend to grab at least every variable that currently exists and grab it like it is. And then when you execute that code, you get all those variables that currently exist. We don't really have variables at this point. We just have what's on the stack. So we have a bunch of words that say, I'm a transformation from stack to stack. And it's kind of hard to say, like, while they're a little tricky. I mean, but this is the trickiness in the compiler stuff. I mean, that's why. Um, well, there are a lot of different approaches you can do. That's kind of why they have all these approaches because they've explored this space so hard. Because it's like, do you want to make everything a closure? Well, that costs you in certain ways. Do you want to do you want to have reserved words for a while, or you gonna make it a word you could define in the language to make your own control structures, right? So the approach we're taking does not lend itself to us defining new control structures. Um, we don't provide enough. We don't capture enough context, and maybe our semantics aren't quite up to the job anyway. I don't know, but if we want a control structure, we have to go program it. Okay, so um, as we are now, we're in that position now. We don't have if, we don't have while, we don't have repeat. So yeah, we gotta build them. um, it'd be nice. All right, hey, welcome, Basie. um, so yeah, I'm not sure. It's like we could definitely go in different directions on this stuff. And I did work on that Elm interpreter a couple years ago and never really quite got it worked through on that stuff. I don't think I had the closures quite worked out or something. But there's definitely a little subtle stuff that goes on when you make these decisions, and we're taking the easy way out. I'm saying this is going to be a compile time construct that will create code that executes the code we wish we could generate at runtime. And there is no way in our current setup to make it define your own stuff like that. You have to write an actual assembly language compiling routine for something. All right, so I think that's what we'll try and do. Now, um, again, because it's this kind of multi-level thing, like one way to test it would be if I want to test that. Well, let's take repeat until. I think it's the easiest one, so let's plan on starting there. Um, I could check that um, if you execute repeat true until, or something like that, or repeat true dupe until. So it would always create a new true to test with and leave it there. It would generate some code. And the code it generates would be whatever the inside of the loop is. We would see at the end a jump if start and then a branch back to the address here. And that would be a legit way to test that we generated the code we expected to generate. All right. Now, is that code correct? That we're not testing, because the only way to know if that code is correct is to make sure it actually runs a loop in some sense that it does. So if I did something like repeat, increment until false, or repeat, let's say we push a 0 on the stack outside and we do a 1 add inside, so we're incrementing, and I want to do that once. So if I push, if I do 0 repeat 1 plus false, or 0, because it's 0 is false for us, until, all right, that code should execute once, because the false means we just kicked out right away. And the increment should leave a 1 on the stack underneath that 0, and we could run that code and then decide if it's if that code actually did what it should. All right, do we need some look ahead to find the ends? Well, that's the trick we're doing, is to not need the look ahead. We're only going to do look back, or patching is really the way we say it, or patch back. No, there's a back patch. There we go. If you say I'm only going to go backwards and fill in corrections, okay? Because I don't know. I mean, like, I could be reading an arbitrarily long file and have to keep track of all this stuff until I find that until statement, and then I'd go back and reread it as I work through it until I hit another repeat, and then I'd read forward again. That would be very expensive. So instead, we just keep track of a little tiny bit of information, like I've got a start address here for a repeat loop, and we don't even need to keep track that it's a repeat loop. We just say, because we know it's balanced, we're just going to keep track of that start on a little tiny stack, control stack. And in this case, the repeat until puts one value on the stack, and then the repeat puts it on, the until takes it off. And so the stack, it just holds one little bit of information, one word, basically one quad word of information, the address I need to patch to or jump to at the end. And so we don't need to look ahead at all. And, and that's, you certainly can do the compiler where you look ahead. All this is like, I think of the as if rule, if it looks like a duck and quacks like a duck, treat it as if it were a duck. We do the same thing here. You could define what it means to compile by pretending you looked forward and found it. But in practical compiling, you probably don't want to do that. Now, you might. I mean, I don't think I can write, 10 nested loop deep stuff and get it right. I'm going to write 1 or 2 nested loops, put it in a procedure, and make it work. So it's not really going to be, thousands of lines unless you got generated code. Okay, so let's see. basically, we're working in this ARM assembly language. So we're trying to generate code for this sort of fourth language, and it's a stack-based language. So all our keywords are like stack transformations, other than like repeat and until, I guess. But most of the operations do work on the stack, and we want to generate code for our. We have a data structure that holds what a routine looks like, and so that's like lists of addresses that go in our code, and our interpreter looks at those and deals with them. So we have a bit of a compiler and an interpreter. We're going to work on the compiler part for this. So I think we did write jump if false, and we wrote jump. So let's go find those, kind of see where we're headed towards. I'm going to move this up. We're going to work on repeat until first because it's the easiest. Okay, and then control. I pulled this out of what was core. So jump if false, evaluate the top of the stack, branch around the code if false, and it's followed by a word. Um, it's followed by the address we want to jump to. Okay, so jump if false, it pops the top of the stack, compares it to 0. If it's 0, it skips the jump. Otherwise, it does well. If it's gonna the true, it's gonna have to move the program counter forward and skip over the address that we're storing to. If it's not, and then the program counter is pointing to the address, and we load the contents of that address is where we want to go to and put that in the program counter, and that transfers us. Okay, and then a jump is much simpler. You're pointing to an address. You're pointing to a word that contains an address, so you load it into the program counter, and that's your new program counter address. All right. Now, I mean, gosh, all these times I see these little if statements like this, it makes me wonder because we found that C cell that does conditional selection or something, but I think we have to jump physically around this kind of stuff. I don't know if there's a quick way, but this is the code we're generating that will do stuff. So we have to make sure that the word following jump if false needs to be the address we want, and that's what this compiler stuff we're doing is gonna work on. All right, and then let's find the control tests. I'm gonna move this over and close a bunch of stuff. We get buried sometimes. Okay, so control tests. Yeah, so we put in a dictionary with junk so we can make sure we overwrote it. All right, and then we put in a definition for jump if false, for push, and N2D. So that's the only stuff we have in our test. And then we define some words. Okay, and then this is the secondary. 1 corresponds to push 7. Address 0 corresponds to jump if false. Well, 7 is considered true because it's not 0. Okay, the target is line 7. I think we count 1, 2, 3, 4, 5, 6, 7, which is N2D. So we skip around this. And I guess this is the program in this case should probably say what it is. Well, you can't really. Yeah, I guess I sort of can. I think this would be the equivalent of if, well, no, it'd be equivalent of 7 if it's true. Let's see, if it's false, we're going to line 7. If it's true, we got a 1, which is a push 42. Okay, so 7 if 42 end is kind of what we're doing here in this test. Okay, so 7 turns into push 7. Jump if basically turns into jump if false, followed by the target to jump to if you want to skip, which is kind of where the end is going to be. And then the 1 is the body, push 42, and then down here we're ending the secondary, so blasting out. Okay, so if you were to compile this, you would get this. And our test is, does the interpreter run properly on that generated code? All right, and then we did a test for if 0. Same kind of thing, except we didn't push 42. 7 to start with, we pushed 0. So let's get this one too. It's almost the same. So here we push 0, which means our statement's false. Then jump if false to line 7, the end. Otherwise, push 42. And so when you run this, we should consume the 0 on the stack and not push a 42 and be to the end. Okay. And we check that. We check that the stack got back to the original place, so nothing is on the stack. Okay. And then this one is a jump, and we don't let you write go-tos in our language, so there's no direct code for this. 05 says jump to line 5, and if we don't jump, we'll push a 17. Okay, so we run it, and we should have jumped without pushing, so we make sure the stack is at the original spot. Okay. So I feel like we've tested. I mean, we haven't done a lot of tests, but we've done some tests on these to make sure that jump if false works for true or false, and jump just does its job. And so if we generate the right stuff, I feel like I think we probably interpret it correctly. So let's see now. um, this is more compiling. Although I could see putting it in control too. Maybe control is the right place. That these are sort of the runtime words that aren't exposed to the user. They're built by this system. We don't let users go around doing jumps to arbitrary places or go-tos or conditional or unconditional go-tos. And so I think that will be our test for this. Okay, now, I don't think we'll need that. So, let's see, push 0, jump if false, go to, yeah. Yeah, so let's get repeat working. Okay, so this test, we're gonna say repeat generates write code. Okay. Now I don't know if I should check the repeat until. Boy, this is. It also makes me want to think at a higher level of like our REPL. We could spit out code and run it through the REPL and decide if the REPL did the right thing. But I think we need to get into the secondary, so it's going to be one of those. Oh boy. Okay, so who else? Maybe it's repeat until. I think we're just going to look at the whole block and get it right. Okay, so I want to find. Let's think about where we have examples. I think our only metas are in compile, right? Yeah, so compile, right. We've got secondary space. And remember, it's built the header for us. Okay. So I'm going to assume the header's there, and I'm just going to check the body of a secondary space thing. So let's get compile tests, because they're going to have a test for that. Okay, so colon, it does a lot. All right, so the trick we've got there is we create a test secondary area, and I'm going to do that same thing for us. We'll definitely need that. Okay, so control tests. Let's do this data. Okay, this is just kind of prologue we need. Okay. No, we're not going to create a go-to secondary. That's the thing. We're going to kind of make it, we're going to force structured programming, no go-tos kind of stuff. Because we're going to provide, if you've got, basically, if you've got sequence if and while, you've got everything you need. And if you have recursion, you don't even need while, because you can make a recursive call. But, as long as we provide those three capabilities, if, while, and sequence, which we always have, they can write any program they want to. So we don't need to go to. Yeah, we could do something, but like then we'd need some sort of label thing. I mean, yeah, I mean it would be a doable thing, but fourth historically didn't, and I don't see any reason to put it in for us. I think we're not going to build weird control structures. If you were doing like a state machine generator, you would probably do something like that. You would have an arbitrary go to because one state can go to any other state, and they don't have to follow any structured pattern. You can have weird little half loops and stuff like that. So, um, yeah, we could. I don't think we will. All right, but I do need this. So I need the secondary area. I'm going to do the same thing I did here. Um, I'm going to load secondary spaces, or a register that we need to point to our secondary area. And this area we're going to fill in with our repeat until. All right. Now, I don't know. I think we can test kind of pretty minimal. All right. So that's where things are going. And then if you call repeat, I don't know what other setup we need, but if you call repeat, somewhere we need a control stack. Okay. But I'm just going to skip over stuff while I figure out this test. All right. So the act is going to be it's going to be a two-part acting, which is a little weird for me. I don't often do that. Act. Okay. The test is generate a repeat. So we're going to assume there was a repeat instruction. And then I don't know if we need to generate the code inside. I think we can skip it. Okay, so I'm going to branch to repeat and branch until, and I think I can say that's going to be, well, until is supposed to pop. I think we can do it like this. We'll just kind of arbitrarily ignore the code that would be integrated in the middle, as long as the loop stuff seems right relative to each other. I think it's probably reasonable. I I can't guarantee it, but okay. And then the assert is, well, we're gonna get this address again. Um, well, we'll keep secondary space. I don't know. Something is getting loaded with this address because we want to go back and see that we generated the right stuff. Okay. Let's see. So the repeat until, um, this code needs to be a target. So it's going to be cell 0. We would have a header in real life, but we're just kind of checking the code. So this would be a 0, and then this would be ignored. So this would actually be instruction 0 goes to itself. And that's kind of it. Okay, I think that's the correct code. Okay, so the first thing in there, well, that's only one instruction, right? There's no there's no code generated for this. It's just tracked, and we generate one instruction that has a thing following it. Okay, so I want to say this code is, all right. Let's load x0 is contents of secondary space. Well, I don't even need secondary space at this point. X0 is this, contents of X0 is probably good enough. All right, so we're going to take that cell. Its body should point to jump if else, because we skipped all that. Yeah, Yeah. So zero being false. So if it's false, it's going to go back to the top and keep going. But in our case, the start instruction is going to be the jump if false because we don't really um, have any body. This will be an infinite loop if you ran it, but we're just checking that the code comes out right. Okay, so the contents of this, now I think I could say load address x1 is, that should be the word address for jump if false. Let's see, what did we do there before? Control. Jump if false. Now, what happened in here? Compile tests. Oh no, control tests. Oh, we only tested. Yeah, this is tricky. We really tested here. We put the thing we said in for jump if false, but in real life, we need the dictionary entry for jump if false. Um, we checked that it ran correctly. But we don't really need a dictionary entry for it is the weird thing. So it's let's hmm. All right. Well, I think it's going to be something like this. The data address, this is jump if false word address, and dot quad jump if false, or did we put a underscore on that? I think. Yeah. I think we decided we could do it in the data in the text area. And we'll make this aligned 3. Okay. This word is what should be in there. No, that can't be right. This has to be over in the compile code. Sorry, control code. Okay, so jump if false word address, that code should be what we see there. And that points to the secondary routine. Load address x1. I think that's right. Okay, and then the second thing, so let's load address x0l test secondary area again. Oh, this is BL assert equal. And then all right, the secondary area, then we need to load it offset. X0 is x0 plus 8. Add it first. Okay, and we're not going to store it, so it doesn't matter to that. That's the contents of the second word, and that should be L. Well, I guess it should be x0. Move x1 gets x0. BL assert equal. Okay. Well, I think this is going to take some thinking through tomorrow. We'll start with this test, see if we believe it, see if we can get it to run and fail. Um, I think we have a little choice in here. We probably could do another level of indirection and make sure it's equal to jump if false. But yeah, let me throw that idea in before we go, I guess. Um, this would be kind of a test that the word address is what it says. Okay, so this value should point to this value, and we're following an extra time to see if that's true. All right, so we'll walk through the test tomorrow, make sure it seems to express what we want, put in the required, um, well, a bare minimum repeat and until code, make sure they're in the meta loop or meta list, and get this thing working. I hope. All right. Well, like I said, I think the control structures are the interesting and challenging part for us at this point. I'm pretty sure we can write something that tests for zero or tests for equals and all that stuff. So they'll be very straightforward once we finish these control structures. I think we just need if, repeat, and while would be plenty if we can find a good way to do them. All right. Thanks for joining. I think we're making progress on this stuff, and tomorrow will be interesting. That's code word for we'll have to debug. All right. Thank you, and have a good evening. Take care. Bye bye.